Hello everyone. Today I'm going to present this paper, Iteration Head, a mechanistic study of chain of thought to you. And this paper is published on NeurIPS 2024. Its authors mainly belong to FAIR Meta AI. And first, since this paper is about the topic of chain of thought, I'm gonna first introduce a bit about what is chain of thought reasoning to you. So there's an interesting finding in large language models. That is, when you need a model to do some inference, and if you simply add things step by step to the prompt within your problem, and the large language model will generate a, a chain of its thinking procedures that is very detailed. And this will totally add to the final answer. Instead of if you do not add this specific prompt of think step by step, the model will probably just generate one single answer here, and it's not guaranteed to be correct, or at least it's not as accurate as when you add this chain of thought prompt. Okay, so here's an example from the paper illustrating what is chain of thought. So the question here given to the model is this simple multiplication problem. And as you can see, if the model directly generates the answer here, it's the wrong answer. But if take it step by step is offered to the model in the prompt, the model will take two intermediate procedures here, and this adds to the final correct answer here. Okay, so what this paper is interested in and focuses on is how exactly does this chain of thought reasoning capability emerges in large language models? So there are two main contributions in this paper. The first is that in investigating the previous introduced problem, that is how COT capability emerges in large language models, they introduced their concept of called the iteration heads that I summarize as a weight pattern that is able to deliver accurate information needed for a position T in the next token prediction task. And this can further enable the model architecture to learn other iterative tasks. And the iterative tasks actually in practice can represent a lot of those reasoning tasks or inferring tasks. So it's a very important capability for a large language model. I will further illustrate this later. And another main contribution is it provides substantial and inspiring experiments. We will also see this later. Okay, so since LLM is all about stacking those transformer blocks, and and this paper will also use the same structure here, which is the transformer block for their discussion and experiments. The authors of the paper uh, re the authors of the paper will treat the readers as familiar with the transformer, but I will still have a brief introduction here. So a transformer block generally contains an attention layer that calculating the attention score of the input. So suppose the input X is some sequence. The attention score will calculate is a function of QKV. The QKV is separately called query, key, and value, which are actually just learned representations of the input X. And by doing this function, you can calculate the attention score here. That generally speaking, it just tells you where exactly should the model pay attention to in the input. And other things in the transformer blocks are just very general things you can see in all those models. That is a feed-forward network. It's fully connected layers plus activation functions. And as you can see from this construction of the transformer block, it is actually very hard for a transformer block to learn an iterative task. And why is that? Because there's no, unlike networks like RNN, there's no internal states that can be memorized by this transformer block. And also, as you can see in this attention layer, what all it does is it since QKV is also the learned representation of the input, what it does is it just uh, performs some cross operations in its input, and this is bounded by a limited number. So it's actually very hard for it to go go iteratively, especially if the iterative steps is a large number. So next, I will introduce how the authors define their concept of iteration head in their paper. So they study this COT emergence in the case that uses two transformer blocks to learn the iterative tasks. And I've introduced that the iterative tasks is a kind of a representation for COT or vice versa. And LLMs are trained on the basic task called next token prediction, which is basically given the previous sentence or previous words, the autoregressive LLM, namely GPT, needs to predict what is the next word, what is the next token in this sentence. And here, since the authors are trying to emulate what an exact LLM does, so this is this experiment or research is in this setting of next token prediction task. And this is how this task is actually like. So we can see there's two sequences here. The first is the X1 to XL sequence. This is the input sequence. And the S1 to SL sequence is the state sequence. So the iterative problem they formulate here is about this state sequence. The the state at time t is equal to an iterative function of the previous state and the current input. So this forms a very easy recursive iterative task for LLM. And in this next token prediction in this next token prediction task here, we have totally 2L. If suppose the sequence of the length of this sequence is L, so we have totally 2L plus 3 input here totally for the LLM. The first token is a problem token, which indicates indicates the information of which which problem this LLM or the two transformer blocks the authors are using here is going to solve. And I will introduce their experiments problems or their design iterative tasks later. And I've introduced that the X1 to XL is the input sequence, and the EOI is a sign token, which stands for the end of input. And S1 to SL is the state sequence. The EOS is also a sign for end of sequence. Okay, so now this is the image from the paper that elaborates on what is exactly the iteration head. So in this image, we have xt as input. PT is called the positional encoding. That is can be easily understand as it just memorize the position of the input. As you can see, it's both T here. So PT just means this input is the teeth input. And for the two transformer blocks here, for the first attention layer, its task is actually to tell the second attention layer some information here. And in this image, the purple blocks here stands for it comes from the residue connection from the input here. So and the red block stands for the result of the attention layer. So we can focus on the red blocks here. The output of the first attention layer is PL plus 1, which is related to this EOI sign, which is the end of input. So the key here for the first attention layer is it's abstracted by the author, and it's easy to understand. I am the end of input, and the query here is, are you the end of input? So there is certain parameters that we can train for the attention layer that get us this uh, the key that means I am EOI, and the query that means are you EOI. So once we get this query and the pair of this key and query, the first attention layer will output this positional encoding of PL plus 1, and this will be told to the second attention layer. So for the second attention layer, it will try to get all the information needed for this iterative function. So that the thing need to calculate the state at time t is the previous state at time t minus 1 and xt. As you can see in this image, the state time t minus 1, which is the previous state, is just the residue. You can just get that from the residue connection. And so the problem is how we can get the xt, the input at the step t. So here for the second layer, the authors aim to get the parameter, namely the pair of key and query that tells the second attention layer here to focus on this PT, which is the positional encoding of the teeth input. So how does it know that it need to focus on the teeth input? They they get from this input sequence here. This is the PL plus T, which is the positional encoding of the L plus teeth input is also an information you can get from residue connection here. And from the output of the first attention layer, you get you get the L plus one index here. So if you do a minus subtraction here, what you get is what you get is when the model is processing this PL plus T PL plus T node in this sequence, it will it this subtraction will tells the second layer that the input information you need is from the T's input by this subtraction, since this gives the result of T. So the key, which is also the answer to this query, is IMPT. So by noticing this PT is necessary for the calculation, it can get some information from this relevant xt, and thus getting all the information we need for this iterative task. And all this weight pattern that those two attention layers can learn to fulfill this operations of K meaning IMEOI, Q meaning RUEOI, and also this for the second layer. All this weight pattern learned is defined by the author called the iteration head. Okay, so the next part of these papers is mostly about various experiments, and I'm going to introduce the most important parts and the most important conclusions here. So the authors mainly targeted on three design iterative tasks, which are the copy task, the parity of the sum of a binary sequence, and the polynomial iteration task. I'll briefly explain what those are. So the copy task, if we go back to this iteration formula, the copy task just make sure that the next state is it wants the next state to equal to the previous state. So it just copies this to the next one. And the parity of the sum of a binary sequence, and this is also easy to understand. The this iteration task wants to uh, calculate the final parity of the sum of this sequence. And the third one, a polynomial iteration task. This is formally defined in the paper, but it's not very easy to understand. So what it basically does is it calculates the nth version of this parity of the sum task. So, or vice versa, I can say the parity of the sum of the binary sequence is the mod 2 version of this polynomial iteration task. So you can think of that this polynomial iteration task is just a harder version of the second one. Okay, so let's see some results of the author's experiments. So the first experiment the authors conduct is on the parity iterative task with L equals to 29. Remind that L is the length of the sequence. And there's also some general settings of the experiments, and I won't introduce them here. But the authors generally generates 1024 sequences for each of those different lengths. So it's a very large data set. And so I think the results will be very representative. So what the result of this parity experiment is here in this image. They show this two attention maps of the two different attention layers. What So we can focus on this two yellow lines here. What this means is, as you can see, this y axis here. The yellow one means the attention score is very high. So for query, this is about like half of this axis. It's about 29, which is 29 or 30, which is nearly the L here. What that means is if you check back this this sequence, the EOI is here, right here at the middle of the sequence. That means for all the S sequence, for all the state sequence, the state token after the EOI sign, the first attention layer will always give attention and focus on the EOI. This means the first attention layer does provide all necessary information, which is the EOI sign, to the second attention layer. And for the second attention layer, what it needs to do is it needs to focus on PT, which is the teeth input. And what this line means is for the second half of the state token, as for second half of the total sequence, which means all the state tokens here, it will focus on the related the first half of the tokens, which is the input. You can see it like it is likely that it starts from 1 here to before the half, which is EOI. So here's like x1 to xl, and here is key. I'm sorry, it's this is key and this is query. The query starts from the starts from S1 to SL, and the key starts from X1 to XL. So this image can confirm that the idea of the author's iteration head is correct. And the second experiment they conduct is a polynomial iteration experiment, and it mainly focuses on investigating the influence on different parameters here. So the different parameters are the embedding dimension and the sequence length. The sequence length we have introduced it. It's just L here, and the embedding dimension is just a general parameter which usually, if it's big enough, it can represent all possible functions. So as we can see here in the plot, as the max sequence length increase, which means the difficulty of this task is increasing. The the red here means the higher accuracy. So as the difficulty increases, it's actually harder for the this two transformer block architecture to be correct. And as you can see here, it's about 10 in the y-axis. If the embedding dimension is too low, there's also a chance that these two transformer blocks cannot get the idea of this the iteration head. And for comparison, they conduct experiments without COT, that is, without this specific design of the weight pattern trained, and the accuracy is almost zero. And with one layer, it means like if it's only with one transformer block, then the accuracy is also not good here. It can only solve the tasks with very few sequence, very short sequence, and so it can only solve easy tasks here. And this is another plot of this. I will not introduce what exactly is this attention PK they defined here, but it generally tells you the same as the above plot. So the final experiment that the authors conduct here is a transfer learning experiment. So they stated that their iteration had the simple two transformer block architecture is actually having a very strong transferability here. So they conduct this experiment. So they are actually transferring from the polynomial iteration task to the parity task. The polynomial one is actually when I introduced this, I said this is a harder version of the parity task. So this is somewhat confusing here. But the explanation from the authors is that since the parity task is here it is like too easy for the transformer block, so there might be other other procedures, other methods that the model is actually referring to, other than the iteration head that is proposed by the authors. So what that means is for a easier task, that is the parity task here, the model actually have some competitive methods that are competing with each other. So this actually leads to a worse worse performance of the model. So after explaining this, we can check the result of transfer learning from the polynomial task to the parity task. And we mainly focus on this orange line and the green line. The orange line is the target task that we are trying to learn. But if we first train, here is 200 according to the authors. If we first learn 200 epochs of the polynomial iteration task, and then we transfer to this parity task, as we can see, the model learns it super fast here. Unlike if we only train on the parity task, we need about 500 epochs to reach the or more to reach the maximum accuracy. But if we transfer from the polynomial iteration task here, we only need about a little more than 200. So this demonstrates the strong transferability of the iteration head like models or architectures. So for the conclusion of this paper, I think this paper is very very strong, a paper of very strong conclusions, very strong contributions, and it also gives us very inspiring results of the experiments. So, and thank you all for today.